Okay, so in the previous video, I gave you this question. So, what is the critical value for 1% significance level? Uh, like, remember, the critical values are calculated this way. Around your belief, you add and subtract something, right? So, but this lowercase z depends on the sample, the significance level, which is 1%, which implies 2.58. So you can just take that number, or you can find top 0.01%, probably top 0.5% value from Excel and multiply the standard error. Then you are going to get upper critical value 81.29, lower critical value 78.71. And then now you calculate the critical value. Then you have to compare that to the sample average. Do you reject or not? It's simple. So your belief is 80. So you are inspecting I-beams. I-beams have to be 80, but you allow plus minus 1.29 millimeters, right? So your margin is 1.29, but your difference is only minus 1, which is within the margin. So you do not reject the null hypothesis. So if the sample average has a difference greater than plus minus 1.29, then you are going to reject and you are going to punish the I-beam manufacturer. So, however, in this case, the difference is smaller than what you allow, so you do not reject the null hypothesis. Okay, so in other words, the acceptance region is in between these two numbers, in between those two numbers, and your observation is greater than the lower critical value, so it's within those two critical values. So you do not reject the null hypothesis. Okay, then let me ask you another similar question. What happens if you use 10% significance level instead of 1%? Recalculate and see how they change. Okay, let me give you the answer. Now the difference is only in here. Alpha is now 10%, so you have to use top 5% standard normal distribution value, which is 1.64, right? So plug that in here, then the new critical values are like these, okay? So, and then in this case, when you change the significance level, what happened here is earlier the upper critical level was 81.29 and lower critical value was 78.7, but it is narrower now. So the margin was 1.2 something, but now the margin is only 0.82, less than 1 millimeter. So higher critical value is more strict. You are more likely to reject the null hypothesis, and you are more likely to punish the I-beam makers. Okay, and like as you can see in this case, now the observation 79 is outside the critical values, outside the acceptance region, so it is rejected. Your null hypothesis would be rejected if the observation is 79. So remember, it was not rejected earlier at 1%, but now it is rejected because the significance level increased. So we verified our mathematical conjectures. By the way, anyhow, we used critical value approach, but also the same thing would happen even if you use p-value approach or t-stat approach. Thing is, I told you 3 different approaches, but basically they are the same thing. Mathematically, they should be the same thing. Okay. Now, what I'm going to do here is I'm going to change the null hypothesis. Now, suppose that I am the inspector and I I obtained some insider information. So whistleblower told me that they are making a little smaller I-beams. So the standard must be 80 millimeter, but on insider information told me that they are making 78 millimeters, right? Which is 2 millimeters smaller. So now I believe the mean is 78 millimeters. Okay, but it is kind of insider information. There is no data. So based on this belief, I start inspection, right? So now the data are the same, basically the same. I collected 400 I-beams and measured their average height, which was 79, and standard deviation was 10. In this case, under under the belief of 78, do you reject the null hypothesis at 1% or not? So you do it by yourself. You may use any of the 3 decision rules. Just make the decision by yourself. Okay. Okay, let me show you the answer. Like you may use t-stat or p-value or critical value approach. So let me do everything. Like so, t-statistic approach. You are going to standardize you believed the actual height was 78, but actually it measured 79. So the difference is plus 1. After standardization, you get 2. Standardized difference is 2. And because we are using 1% significance level, the threshold is 2.58, which is wide. You are very generous. 1% is very low significance level, so you are very generous. Okay, so as a result, the observed standardized difference is within the threshold. It's not greater than the threshold, so it is okay. Your belief is not rejected. Okay, similarly, the p-value based on the t-statistic, the p-value is the probability outside plus minus 2. So you can obtain 4.5%, which is easily over the significance level. So, like, even if you use the p-value approach, still you are not going to reject the null hypothesis, as it should be, right? So, p-value t-stat approach cannot reject the null hypothesis. Finally, the critical value. This is the critical values are around 78 now. 78 is your new belief, and plus minus 2.58 standard error, which gives you these numbers. And remember, your sample average was 79, so 79 is within this interval, between these two critical values. So again, your null hypothesis is not rejected. Your observation is close enough to your belief. Okay, so no matter which method you use, you are going to get to the same conclusion, not rejecting the null hypothesis. Okay, so then what I wanted to tell you here is, in this example, what you can find here is, remember, the data are the same. I gave you the same number from the data and same significance level. The only difference from the previous example, so like go back here, in this question, we could not reject the null hypothesis. And here, we cannot reject again. That means when you believe the true mean is 80, you keep that same belief. You keep that belief. You believe that the I-beams are correct. But now, if you change your belief, you keep the belief again from the same data. So even from the same data, depending on your belief, how you interpret the data is different, right? If you start from the belief that the I-beams are correct, you maintain that belief. But if you start from the belief that the I-beams are wrong, then you also keep that belief. So this is a very unique and strange property of hypothesis testing, or So setting up the hypothesis is really important. So what you use as the null hypothesis is really important. It changes the decision totally. So be careful when you use hypothesis testing. Understand the importance of the null hypothesis. Okay, that was, and this is the last example that I prepared for this chapter. So now I will assume that, so you developed a new vaccine for COVID-19, and of course, hypothetical data. And suppose that your vaccine is effective with probability 80%. So, like a randomly chosen person get a shot, get this vaccine, and after a certain period of time, if the person tests for antibodies, then with 80%, the person has antibodies against COVID-19. So 80% effectiveness is my belief when I develop this vaccine. Okay, so we are going to test my belief. Probability of having antibodies against COVID-19 after getting this vaccine is 80%. Probability of success is 80%. Okay, we are going to test this one. And as you may have expected, this is a binary distribution. So everything is the same, but we are going to use binary structure. First, the probability equals the mean. So we may use the same framework in this question, in this example. Okay, and another thing here is your belief 80% not only fixes the mean, but also fixes the standard deviation. So in our earlier cases, the normal distribution is parameterized by the mean and the variance. Mean is implied by the hypothesis, the belief, but standard deviation was not. So we borrowed the data, the information from the data to impute the standard deviation. But now, the standard deviation is also implied by your belief. So you have to use the belief to calculate the standard deviation. That is the only difference. Okay, keep that in mind. So remember, binary distribution has standard deviation of this form. So under your belief of 80% probability, the standard deviation must be 0.4, right? So your belief implies standard deviation is 0.4. Okay, then using this standard deviation and your belief about the mean, you are going to approximate the distribution of x bar to a normal distribution with mean 0.8 and standard error 0.4 over square root n. Remember this. Of course, n must be specified by the data. The sample size is obviously from the data, but everything else, the p here implies mean and the standard deviation. Okay, now then, from the data, what you observe is 100 people, 100 vaccinated people, and antibodies are found in 75 cases out of 100. What is the p-value? Calculate. Okay, let me show you the answer. First, we calculate the sample average. So this is the data. Data is simple. From the data, the sample average is the sample probability of success, which is 75%. So x bar equals 0.75, and your belief is 80%, 0.8. So the difference between the sample and your belief is minus 5%, minus 0.05, right? So standardize using standard deviation also implied by the belief, right? So this standard deviation is affected by 0.8. So 0.4 is used here. So after standardization, the difference, the t-stat is minus 1.25 and transform that into p-value. We calculate probability outside plus minus 1.25, which you are going to get 21.13%. So, and remember, up to here, I did not give you the significance level, alpha. Alpha is not needed to calculate this one, either p-value or the t-stat. Okay, then now you can do this way. At which level can you reject the null hypothesis? Remember, the null hypothesis is rejected if the p-value is smaller than the significance level. But here, in this case, p-value is too big. It's already 20%. So none of them can reject the null hypothesis. The answer is E. Okay. And then next, critical value approach, which is a little different because you have to specify the significance level and use 5% significance level and calculate the critical values. Remember, we are using binary distribution. Okay. So it goes like this. Your belief is 0.8. That is the center. And around that, because you are using 5% significance level, that implies 1.96 in this value. Right? So 1.96 times standard error. And also in this standard error, you are using the standard deviation implied by the belief. Everything else is the same. So pretty much the standard things like belief, your belief, and significance level, sample size. So plug in those four numbers and then calculate them. Then you allow plus minus 7.84% margin. Alright, so if the difference between your belief and the data is within plus minus 7.84%, you are not rejecting the null hypothesis. So what is the conclusion? The answer is no. We already learned we cannot reject the null. P-value is too high. Or the critical values, our sample percentage was 75%. Sample probability was 75%, which is contained between these two numbers. So it's in the acceptance region close enough to your belief. So you cannot reject the null hypothesis. The answer is no rejection. Okay, so this is how you use the hypothesis testing for binary variable. Okay, this is the end of this chapter. So in this chapter, we learned the basic mechanism, how to implement, how to make the decision, right? But what we didn't do is, like, how good that is. So how accurate your analysis is. In the next chapter, we are going to learn error probability. What is the probability of making a wrong decision, right? And additional topics will be covered in the next chapter. Okay, I hope you enjoyed this video. It can be confusing, but it's interesting. Anyhow, we will continue in the next chapter next week. See you there. Bye.